Okay, kids, so we're back, and we're going to do section 3.3 and 3.4 together. So we're going to talk about gravity. That's really important. And take a look at universal gravitation. And then, oops, what was that? And we're also going to have a look at the satellites. Like the moon is a satellite of the Earth. The Earth is a satellite of the moon. The Earth is a satellite of the sun, I should say. We've got artificial satellites zipping around our planet for telecommunications, International Space Station, and who knows what else is up there. I know there's a lot of garbage up there, junk from abandoned technology that's orbiting our planet Earth. It's becoming quite a problem. So let's first start by saying, look, let's get back to studying gravity that we looked at a little bit in grade 11, and we're going to look at universal gravity. So let's say this is a large celestial object. There's the center of it. Could be a sun, a star, a moon, planet, what have you. And this has a mass m1. And over here is another object, right? There's its center, right? And it has a mass m2. And we're going to measure a distance from center to center between the two, and I'm going to call that distance R this year. Last year we used a D. We're going to call it an R. And we learned last year that along this line there's a force of gravity, right? Force of universal gravity, big G. What's up, big G? So the force of gravity on object 1 because of object 2. And because of Newton's third law, we're going to have the force of gravity on object 2 because of object 1. So these are definitely Newton's third law pairings of forces, definitely. And if we remember from our grade 11 work, we were able to find the magnitude of this force. The direction is always, as we show here, center to center. Big G, the universal gravitational constant, mass of the first object, mass of the second object, all over that distance between them squared. And you probably remember what G is. 6.67 times 10 to the negative 11 newtons meter squared all over kilogram squared. We did this last year. So when you're looking at this function here, right, it's definitely a function which is an inverse square function, right? However you want to write this. It's an inverse square function. So we say that the strength of the gravitational force follows the oops, let me make sure I can do this right. The inverse square law. That's what it follows. We've seen this function in math class before. And we know what this function looks like if we were to graph it, right? We'd have the magnitude of the force of gravity, universal gravitation right there. And here we'd have R. And the inverse square function looks like something like that. Okay, probably not the best drawing in the world, but nevertheless, that's what it looks like. So what I want you to do now is a little bit of research. And I want you to find the magnitude of the force of gravity between the Earth and our moon. All right, so I gave you that value. You're going to have to look up the mass of the moon. You're going to have to look up the mass of the Earth. And you're going to have to look up an average because it does change slightly. It's not a perfect circle. I'm going to tell you right now. It's more of what we call an ellipse. An ellipse, an elongated circle. Okay, but there is an average distance center to center that you can look up and find. It's in your textbook. But if you want to use the Google or whatever you want to look up, go ahead. And then the distance between them there. So pause the video and then find out what you get and then compare it to the answer. So pause the video now. Okay, so I really hope that you pause the video and now we're back and you plugged in all the numbers that you found because you are in grade 12 now, right? You can do some of this stuff on your own. 2.0 times 10 to the 20 newtons is the force between them. And I hope that's what you got. Okay, I hope that's what you got. So we're going to continue now with the next part of this gravity discussion. All right, so let's think of this situation here as we continue our gravity discussion. Let's say this is the Earth, okay? And the Earth has a certain radius. It's pretty constant. The Earth is not a perfect sphere. It's kind of squished downward from the poles so that it's kind of widens out at the equator. So if you were to take a look at the Earth's radius, it does depend on where you are ending your line, but for all intents and purposes, it's pretty close to a sphere. And let's say that there's an object on the surface of the Earth, and we're going to call this O for object, and it has a certain mass, MO. And this is the Earth right here. Okay, so let's write that down. This is the Earth, and we'll say that the mass of the Earth is ME. So we have Mo and me and Mo. Okay. So what we want to do is we want to find the force of gravity on this object. All right, we want to find the force of gravity on that object. Well, since it's on the surface of the Earth, and the surface of the Earth is certainly part of our universe, we can see that I can use this equation right here, because this is the equation for universal gravitation. So it works anywhere in the universe. The surface of the Earth is part of the universe. But we can't forget that since it's on the surface of the Earth, we can also use this equation. All right, this is the force of gravity on an object near the surface of the Earth. Well, kids, physics has to be consistent. You can't get a different answer depending on which equation you use. So these have to be equal to each other. Or another way of saying that is this equation and this equation must give the same answer. Now I notice I made a little mistake here. I got to put the absolute value signs here and here, so please forgive me. And that's why I got rid of all the vector signs. Okay, that's why I got rid of all the vector signs. So these equations have to be the same. They have to be equal. So that means if I go through here, I can cancel this out. All right. And I can now rearrange this equation that I have right in front of me. And I can get the magnitude of the gravitational field strength near the surface of the Earth is equal to big G, the universal gravitational constant, times the mass of the Earth all over the radius of the Earth squared. Let me do a better, oh, that's an ugly E. I have to fix that. Blah, 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 blah. Okay? So in grade 11, I just told you this was 9.8 newtons per kilogram. All right? Now, what I'm telling you is, right, that this 9.8 newtons per kilogram that we talked about in grade 11 last year, it comes from this equation. It depends on the universal gravitational constant, right? It depends on the mass of the Earth. It depends on the radius of the Earth. So what we can now do is come up with a general equation. Oops, let me use a different color there. and say, if you ever want to calculate the gravitational field strength when you're on the surface of any planet or any moon, right? You can use this equation right here. So let's say instead of the Earth, you've got Mars, and you want to find out what the gravitational field strength is. Oh, I want a different color. What the gravitational field strength is on Mars. Well, you would just use the universal gravitational constant. Now, the mass of Mars, right? We're not doing the Earth anymore. And now, here would be the radius of Mars. So bingo bango, you've just calculated G for Mars, and you can do that for the moon, any place. All right? And it's even better than that. It's even better than that. Watch this. Let's go back to the Earth. So we're back to the Earth. But now, instead of wanting to find G right on the surface of the Earth, what about if I wanted to find out the strength of the gravitational field way out here? What's G when you're really far away from the Earth? You can still use this equation. It's still big G, universal gravitational constant. It's still the mass of the Earth in this situation because we're dealing with the Earth at the center here, right? And we always measure to the center over r squared, except r now is not the radius of the Earth. R is how far is this spot in space away from the center of the Earth. And you could find G away out here. I think by looking at this equation, you would quickly realize if you've got a bigger r than the radius of the Earth, G must be weaker out here. And it is, right? It is. So very, very useful equation. Okay, so now we're into the next section, right? Talking about satellites. What's a satellite? Well, it's an object that orbits a planet or star. Now, the satellite usually has a smaller mass than the planet or star that it's orbiting. Like the moon has a much smaller mass than the Earth. The Earth has a much smaller mass than the sun. And all, of course, all those human-made satellites orbiting our planet Earth are much smaller. Okay, now technically, if you start studying physics more, get into more advanced physics, you will eventually find out that what I'm showing you here is a good first pass at this. It's a very simplified version of it, but for our purposes, it'll work. It's a good starting point, but it does get much more complicated. But that's okay. That's for future learning, something to look forward to. The other thing is we're going to assume that the satellites are undergoing our old friend uniform circular motion. So we're assuming that they have a constant speed. That's a pretty good assumption, even though I'm going to be honest with you, it's not true. Pretty close to being true, but it's not. For example, as the Earth goes around the Sun, its speed does vary on its orbit. Okay, but for us, it's a good start. Speaking of its orbit, it's not a circle, it's an ellipse, uh, which is like a football. It's an elongated circle. You probably learned about that in math class. But for us, it's a good start. Even if it's an ellipse, it's pretty darn close to being a circle. Pretty darn close to being a circle. So we'll go with it. We'll go with it. Okay? So let's say you've got some object here. It could be a star, whatever. It's a large, massive object. Okay? And then around it, you have a path, an orbital path that an object moves along, and we're going to call that the orbit. All right, and it's zipping along here. Okay, so I don't know. Let's say it could be a human-made object. Could be like a satellite, maybe, for telecommunications, zipping around our planet Earth, right? And it's got a much smaller mass. So we're going to, instead of having big M, like the big M for whatever's in the middle here, planet, star, whatever it is, it's going to be little case m. lowercase m, for a satellite. And it's undergoing uniform circular motion, so we can say that right at that spot right there, it would have a tangential uh, velocity or speed, and the velocity would change because its direction changes while it's in orbit, but the speed would remain the same as it's zipping around here. All right. And the other thing we need to remember is we're going to measure a distance from the center of this star or planet, what have you, out to the orbit, and we're going to call that a radius r because the orbit is circular. That's what the assumption we're making. Now, if we were to draw a free body diagram of this satellite, there would only be one force acting on it, and it would be the force of universal gravitation. And I even know the direction of that force because that force is what is causing, you guessed it, centripetal acceleration for this satellite as it's zipping around here. So remember, centripetal acceleration is always pointed towards the center as it's moving around. Here we had a lot of work on this already. So if you need to go over any of the centripetal acceleration stuff, now would be a good time to pause the video, maybe go back and look through your notes from before. Okay, so let's continue here. Let's say we want to find the net force acting. Oopsie, let me fix that. Acting on this object. Okay? Well, there's only one force. It's the force of gravity. And there is only one acceleration. It's centripetal acceleration. All right? Now, we know the direction of centripetal acceleration. It's towards the center, and therefore the force of gravity on this satellite is always towards the center. So let's just worry about the magnitudes. Okay, let's just worry about the magnitudes. So here we have G, big M for the mass of the object in the middle, star, planet, whatever, and little m, mass of the satellite, all over this r that we talked about, the radius of the orbit squared. And that's going to equal little m, the mass of the object undergoing the acceleration. And remember what the magnitude of centripetal acceleration is. It's v squared all over r. So I hope you remember that v squared all over r. And we're going to continue with our math here. And we notice here that the m cancels, right? That m cancels out. And also, one of these r's will cancel. So this will be reduced from r squared to r, and this whole r will be canceled. And that leaves us with g, mass of the massive object in the middle, what the thing is orbiting, right? All over r is equal to v squared. So what does that mean? Let me bring this up over here. Continue right there. Okay? What does that mean for us? Well, it means that there's a connection between how fast you're going in orbit and how far you are from the center of the object you're orbiting. So if you take a look at this, if you have an R that's very small, right? If you have an orbit that's very close to the surface, say, so R is decreased. Well, if you want to orbit, let's say a satellite wants to orbit very close to the planet, our planet Earth, right? If this is very, very, very small in the denominator, that means this quotient gets larger and therefore your velocity is increased. And the opposite would also be true. If you want to be in a stable orbit that's got a huge R, very far away from, let's say, the Earth, some satellite way out there, okay, then, and you want to stay in that stable orbit, with R getting bigger, this becomes smaller, and your speed in your orbit that's required to be in that stable orbit is smaller, right? Finally, for this part, if you want to calculate what that speed is, you just find the square root of both sides. And there you have it. There you have it right there. Okay, kids, so next part of this is called apparent weightlessness. Apparent is the key word, apparent weightlessness. So objects, satellites in orbit are said to experience apparent weightlessness. Now, I've connected a video to this, but you see these astronauts. Let's say you got these astronauts and they're in the space station, right? So the space station is in orbit around the Earth, right? So let's take a zoomed in look at this. So here he or she is, these astronauts, and you notice them floating around, and if they let go of an object, it just sits there and kind of floats around. It doesn't fall into any of the walls. That's called apparent weightlessness. It's not real weightlessness because they're still experiencing the gravitational field of the Earth, but it's apparent weightlessness because it doesn't look like anything's falling, and I can float around in here. Well, you got to remember something here that the space station is undergoing uniform circular motion. So therefore, the space station and all of the things in the space station are experiencing a constant acceleration, which would be centripetal acceleration. So that means the space station itself, the person, if the person, let go of a tuna fish sandwich, whatever, they're letting float around in there, they all are experiencing a centripetal acceleration that's constant. Well, we've seen constant accelerations before. Look, let's say you have an object that is dropped, and it's dropped on the planet Earth. So you have an object in free fall. What does free fall mean? Well, it means this object is dropping, falling under a constant acceleration, which we know is g. So if an object is experiencing a constant acceleration, just like any object that you would drop when you're on the surface of the Earth, and we call that free fall. So free fall means experiencing a constant acceleration. We can say the same thing here. We can say that the objects are in free fall as they orbit. So if you could have someone, like I said, in the space station orbiting the Earth, they are experiencing free fall. And that's why they're seeing all this. And by the way, if you were on the planet Earth and you were in an elevator that was free falling, let's say someone cut the cables, you would be experiencing exactly the same thing. And we're going to look at that next. All right, so let's draw an elevator here. Let's draw an elevator. So here's the elevator, okay? And on the elevator, I'm going to put a scale. Put little markings on it. This is a scale that is used to measure weight. Scale to measure weight. And we're going to put an object, hang it off the scale there. So if I draw a free body diagram of that object, it'll be the force of gravity on that object and the force of the scale that's holding it up, which that force of the scale gives us a measurement of its weight. Okay? So let's assume in the first situation here, that the elevator is moving upward or downward or standing still. It doesn't really matter. Let's just declare that it has no acceleration. So it's got a constant velocity. Could be zero, could be upward, could be downward, doesn't matter. If we apply Newton's second law onto that mass right there hanging off of this, we'll say, well, we got force of the scale plus force gravity is equal to mass times acceleration. And let's use our old trick and let up be positive. So we're going to call this positive W. And the force of gravity is in the negative direction. We're going to call that negative mg. And there's no acceleration, so this is 0. So we get the fact that the weight is equal to the force of gravity, which is something you learned way back in grade 11. So that's just a starting point for us here. That's just a starting point for us because we're going to change things up now, okay, to make this work. We're going to change things up. Let's say now in this new situation, so this is a new situation now, okay, we've got everything like we had before. We got the scale, we got the elevator, we got the object hanging off the scale, right? But now, Wile E. Coyote knows that the Roadrunner's in here and is going to cut the elevator string, cable, I should say, so that the whole thing falls in free fall. That means the elevator, the scale, the object handing off the scale, they all have an acceleration, which is, you guessed it, the acceleration due to gravity. All right, but we can still draw a free body diagram on that object hanging off the scale. So it would be the weight, the measurement we get off the scale, and down here it would be the force of gravity because we're still on the planet Earth. So if we apply F net equals ma to this, we would still get force scale plus forced gravity is equal to mass times acceleration. That would still be true. Now let's use our old trick here. Let's use our old trick and drop the vector notation. Say, okay, well the scale is going to give me a weight reading, which is positive. Force of gravity is mg, right? Force of gravity is mg. I put the negative sign out in front here to give me the direction. All right, and that's going to equal mass times the acceleration. So let's rearrange this equation. I'm going to bring this to the other side. It becomes positive, right? Well, what's the acceleration as this object is in free fall? It's g. And what's the direction of g? Negative, downward. Look, we get that the weight registered by the scale is 0. You have elevator apparent weightlessness. Exactly the same thing to what an astronaut, what he or she is experiencing in the space station. So if someone cut with the scissors here, cut the elevator cable, and you would be in here, right, in the elevator, and let's say you got yourself a tuna sandwich and you let go of the tuna sandwich while you're in free fall, it would stay right there because the elevator is falling, the tuna sandwich is falling, you are falling. It would be exactly the same as when you are in uh, the space station and you are undergoing apparent weightlessness right there. So that is our look at these last two sections of Chapter 3. I hope you got it. If you don't, you know, you can always ask me questions. I hope you have a great day, and bye-bye.